All right, guys. There we are going to consider our question paper, which is working on kinematics, the paper that we wrote in April 2024. So we're going to consider our question number one. So we're given the first part, three cars A, B, and C leave the fork of the road as shown by the diagram in Fig 1 below. So this is what you're given. We are given the three cars A, B, and C. So on our diagram, as you can see, that's our car A at 160 kilometers per hour, then B at 110 kilometers per hour, then also C, which is at 100 kilometers per hour. Then these cars are being separated each by 120 degrees. All right, so this is going to be also 120 degrees in between here. Remember, 360 degrees, a complete revolution. So you are going to subtract these 120 that we are given. We subtract the 120 and another 120. You must obtain the 120 there. So meaning to say, these are separated at 120 degrees from each. Okay, the A from B, the A from C, C from B, the B from C, and so on. So we had a diagram there. Let's consider our question. In this case, you wanted to calculate the following: 1.11, the velocity of car B with respect to car A. So take note, we are working with the B with respect to A. I'm not gonna change the concept that I used on the introduction so that we use the same concept in answering this part, unless if you have another way. There's so many ways, like I said before, of answering these typical questions. But I want us to consider with the introduction part that I talked about so that we do work with the same concept. If you're working with that, we just use that same concept. All right. In this case, we've got three cars, remember? So I'm just going to have this, remember our North Pole. So you're just going to have something like this. There are three cars that are given there. The A, which is at 120. This is our A. Just going to leave this speed, then we use it when calculating. The C, which is somewhere here, separating A with 120. Then we can see that B is direct into the south line in this line of the south. That is where our B is. So that is A, B, and C. All right. So with this, it can be easier to interpret what is happening here. These are separated. Remember, these are separated at what? At 120 degrees. So this is 120 degrees that we are given here. The 120 degrees also that we are given here. The 120 degrees that we are given here. So we are working on the first part of our question. It is a condition that we are working with the car B with respect to that of A. So in the latter case, it is going to be of this nature. Velocity that we're going to have of B with respect to A. Remember what I said on the introduction part so that we maintain the same thing. I explained that you must turn what is with respect to it is B with respect to A. So this is what you're going to do. You turn this A. So you are going to turn the latter part, which is A, and add it to what? To B. Just like that. So you turn A, then you add it to B. You can use the normal way that it is. But I want to explain that also correcting the part that we had from our memo, because that was an error that was indicated. They had this going down, which is true, and also this going down, which is true. So at the end, this carries a negative, and this also carries a negative if you are to use that part of the components. But I want to avoid that because we introduced another way from the previous case. So from the way that I introduced, I said you're going to turn A and add it to B using the components. All right. So this is what you're going to have. This is our A. We need to turn this A as it is. So we're going to have our A this side. All right. We have turned our A. So we're going to have our A this side. So this is where our A is. So we are no longer working with this A. We are no longer working with this side of A. If you use this method, you're now working with A this side. But the question that we are going to need is to know what is the angle that is separated from the horizontal to the B and to the A. We need this angle going to B and also the angle from the horizontal going to A. Those are the only two things that you need. So how are we going to note about these angles? All right, we can note about these angles. Remember, these were 120, 120 that we are given there. So this is easier to work with. Remember, we have removed this part. We're no longer working with this part. I'm just gonna leave the smaller part just to show us where we are coming from. So we are now having our A this side. So at the end, like I said, we need the angles to A and to B. Okay, so from the horizontal going to B, as you can see, this is a straight 270 from 90, 180, 270. So this is at 270 degrees at B at 270 degrees. That is the angle that we are seeing here, 270 degrees. All right, let's move on to A. How are we going to note this angle that is at A? We can use or we can work with this angle that is at this point. It is up to you because that is, okay, let me put it this way. Let me remove this part so that you understand. Remember, this was a 120 from where it was, but as we just need the concept where A is. So this is what is happening here. This is simply a straight line that we are given. All right. So out of that straight line that we're given, this one, the 120 is going this side. This 120 is going into the other side. Okay, we've got something like this. This is our 120 like this. So the 120 is exceeding. There is a 90 that we have here. So it is going to be 120 minus 90 degrees. All right, so that is going to give us what? 30 degrees. So meaning to say there is a 30 degrees that we are having in between this part here. There is a 30 degrees. What is the purpose of this 30? This 30 degrees that we are seeing here is the same as the 30 degrees from our vertically opposite angles, guys. This is the same 30 degrees that we are seeing here. So this tells us that if this angle is 30 degrees, therefore the whole of this angle going to A from the horizontal. Remember, we want from the horizontal. This is our horizontal. So the whole of this angle going to A like this, up to A like this, it is just going to be 360 minus this 30 degrees. You're just going to remove that 30. So this is 360 degrees to A. So we are taking these angles, sorry, that's 360 minus this 30 degrees, which is going to be what? 330 degrees. So this will be 330 degrees. So I want you to see something about this method. It's just going to be lengthy according to this diagram that we are given, but I just want to maintain what I explained before so that we do not fall out of track. So this is it. With this part, I said we are going to work with the horizontal components. The horizontal component adding everything, as you know that if these angles are taken from the horizontal to the part that you're working with to A to B, you are going to simply add. There's no subtraction. You just add. The answers will just be direct as what you're supposed to have when you're operating using the sign. So in this case, we do not going to use part of the sign concept. All right, remember our A is at 160 kilometers per hour. And our B, it was at 110. All right. So this is our B at 110 kilometers per hour. Let's take our horizontal components. So we are going to take, like I said, everything that we are given here, the A and the B, just adding. So A is 160. Remember horizontal component with cos. So that is 160. Cos the angle from the horizontal back to A. This is the whole angle of what? 330 degrees. So that's cos 330 degrees. You add. When you take from the, you just add, all right? So you're going to add B's, which is at angle of 270. So that is B at 110 cos 270 degrees like that. That is the way that I explained before. And this is what you're supposed to have. You're going to obtain 138,564 kilometers per hour. All right. This is, remember, horizontal. When it is positive, you are going to the east. So like I said, you can work with a part of the components, which is fine. If you are working with those components, I mean, if you are maintaining the diagram the way that it is. So the error now that we had, let me explain. This part was fine on the horizontal component from your formula sheet. I mean, from your memo, everything was okay. But now, if you consider the vertical components, because everything we're just going to take as it is. When using this method, you just take as it is. Just put a sign this time. So that's 160. Remember, vertical, use sign. Sine 330 plus 110 sine 270 degrees. All right, there we have got our vertical component, and that was going to give us negative 190. This was supposed to be negative 190 kilometers per hour, which is vertical and negative. You're going to the what? To the south. So this is to the south. So the error now with our memo was on this part, using the method that they were working with, which was fine. Like I said, I'm just avoiding these too much methods here. They took this part of components, which is fine, in this direction. That is given like this. If you consider A and B, you're just gonna take it this way. Then they took it like this. All right, which was fine, because as you consider the vertical, it is supposed to be like this. The indication that we are seeing is that we are going down. Whenever dealing with the relative velocity, you must consider how you are moving. So that direction is important. So this was going to be a negative going down, and this also being a negative. All right. So on the calculations part, that is where the error was going to be. You just need to work out that part and correct, so that you are not going to have a challenge. So if you're working with the angle of that, it was supposed to be negative. You're supposed to use it as a negative because the vertical is going down. So you use it as negative 160 sine of 30. Then this one as a negative, it's a straight vertical as it is. So it's going to be a straight minus 110. So that is what you're supposed to correct on that part. All right. Just make sure you do correct that part from our mem. Actually, for science, these guys, they I don't know. It's not like the first time. I do not know when it comes to the science. I do not know how. Are they not taking much time working on it or what? Because you see a lot of errors happening. Just some minor errors that you just see. All right. So anyways, guys, let's see. Just gonna correct on that part. So that was supposed to be a negative 190, and this being a 138.564. So with these, now we can consider resultant that we can have from these two, the horizontal and the vertical. So you can see that at the end, we're going to have something like this. Our horizontal is positive, which is to the east. All right. Then vertical is negative, which is to the south. So we are working with these two poles, the east and the south. So you're going to have our diagram in this quadrant like this. All right. So that is the horizontal 138.564. Then the vertical, which is at negative 190. So these were the two. You find your resultant and also the angle. So the angle is from the east going to the what? To the south. Or you can consider this one between, which is south going to the east. Maybe you can name it alpha. It's up to you. But working with what is inside of the diagram, you can work with that direction. All right, so there is just velocity, but you can also work with the direction. Remember, the direction is important also. So let's have our resultant from that, or the velocity that we are going to consider. All right. So this is the square root of the horizontal component squared. So we've got the horizontal component. All right. Then we also consider the vertical component. That's a negative 190 there, or you can just write as it is 190. There's no need. All right. So that was going to give us at the end 235,159 kilometers per hour. So that is the idea there. Then if you are to consider the direction, it's simply from our arctan, you have got your direction. So which is theta is simply arctan opposite over what? Adjacent. So that's 190 over the adjacent of 138,564. So that will give us 53,897, which is our direction. So meaning to say the velocity of B, that is with respect to A, was going to be 235,159 kilometers per hour. All right, that is at, if you consider the direction is east to the south, so that is east, 53,897 degrees going to the what? To the south, or if you consider this alpha, it's up to you. So you'll see that there are so many different ways, but out of those different ways, we must have the same thing. We must obtain the same thing. So the only part that we just need to correct, if you are using the method that they wanted to use from your memo, if you are using that, because there are so many ways that you can apply. Just correct the part of the vertical component there. Then you'll be on the same page. Whatever that you're going to have later on is going to be what? Is going to be correct. All right. Then let us consider another part, which is 1.12. So in this case, let us see what we have this time. This time, they need us to calculate the velocity of car B with respect to that of C, B to C. All right, so consider B and C, these two. Let me just use this side since that is where our major part of, okay, but here we have our diagram here, no problem. Just gonna use it here because already we interpreted a lot. See, all right, so let me just save it this way. That is 1.12. So we are going to need B with respect to C. So just like the previous case, what are you going to need to do? We are going to turn C this part. So you turn C, add it to what? Add it to B, just like that. So our focus is not on A, just like what we had before, but our focus is with the C and B. So already on B, I'm not going to change anything because we are relating to B. So to B, guys, is the one that I'm removing now. I'm not going to change anything on B because that was a 270. The only part that we are going to work with now is the C. So this also part of A, we're just going to remove this part. Let's see what we can do if this part is not there. Remember, this is where our A is, where our A was, I mean. So let us just not work with this A and focus with where C is. So we're going to turn this C, just like the previous case. So if we turn this, we are going to see it on the other hand here. On the other hand. So this is where our C is. So meaning to say we are now considering this C. This is now our C. But as we do know, just like the previous case, we must take these angles from the horizontal using this method, from the horizontal. So already B is taken from horizontal 270. What about C? This angle was given as 120 from that part that we had. It was a 120, the whole of it that we had. You're going to say that this also is 30 degrees from that part that we had. So that was 30. So these are same, guys. Whatever that you're seeing here, remember this one was a 30, 30. It's going to be the same thing. This one will be 30, considering the vertically opposite angles now to say these are vertically opposite angles. So if this is 30 degrees here, it means also there is a 30 degrees here in between from our vertically opposite angles. If this is 30 degrees here, this one is also gonna be 30 degrees. Why are we talking about this angle? So that we can calculate the whole of this angle from the horizontal to what? To C, because our C is now this side. So it is simply 180 of the straight line plus this 30. So 180 plus 30 is what? That is 210. So we now have the angle there. I don't know which way we're going to use just to obtain this angle. It's up to you. There are so many ways that we can actually work with. So once you have got these angles, you can calculate your horizontal components. So B, that is, all right, let's take our C, guys. Our C is 100 kilometers per hour. So this is our C, 110 kilometers per hour. All right, so it's going to be 110 at B. So that's 110 cos, remember horizontal, the angle that is affecting B is the whole angle from the horizontal, this whole angle, this one going to be, which is 270. It's not going to change. Plus you add, remember you add. So you're going to add it to C. So you work with this one for the say, which is 100. So that is 100 cos of what? Cos 210. The angles taken from those angles. So that is 100 cos 210. You combine everything that you are given there. That was going to give you the horizontal part of this. So it's just the matter of workings that you are using, but you must have the same thing, like I said. So this was going to be minus 86,603, which is what? Kilometers per hour. All right, that's kilometers per hour there. Then with the same part, vertically, you're just going to use as it is. Nothing is going to change, just the sign. So this will be 110, a sine of 270 degrees plus 100, a sine of what? Of 210 degrees. As it is, you just combine, just like what we had before, you obtain the vertical component, and that was going to be negative 160 kilometers per hour. So on this one, they obtained the same negative 160 kilometers per hour. But if you consider the working, it was still on a wrong interpretation because they were having a 30 degrees this side. It was supposed to be like this. I just want to interpret what your memo wanted to explain. They took the 30 degrees, which is this side, then you consider this as our vertical component is still in the negative. So it is supposed to be on your calculation, if you consider the vertical component, it was supposed to be a negative, which is minus 100 sine 30 degrees. Minus this one is already a straight vertical, as we can see. So it's still just going to be minus 100. There's no need for sine this. There's a straight vertical that we are having. So that was going to give us what? The same part that we are seeing there, which is what? Negative 160. So we're going to obtain negative 160 in our calculation. So we just have to be careful in your calculations. Just make sure you do work with your calculations properly. All right, so that's it, guys. If you wanted to use that part, but they obtained now this negative. So you'll be wondering, where are they obtaining this negative? While the calculation there is not giving a negative. So it was just that, like I said, guys, they are not revising this thing. I don't know what is happening. They need to work with much, they're not putting much revision, especially for this science. I don't know, guys. If you check, let's just hope it's going to change as time goes on. All right. So with this, we are going to interpret, remember, horizontal to the negative. It means we are going to the west. Vertical to the south with the negative. So we are going to consider where the west is and where the south is. So that is our diagram is going to be in this quadrant at the end. So that is where we have our horizontal negative 86.603 and negative 160 in the vertical. So we can obtain this arm and also the theta, which is the direction that you're going to have from west to what? From west to south. As you can see, we are moving from west going to the south according to that theta that we are given. So that's it. Our r there being the square root of the horizontal component squared, negative 86.603 squared plus the vertical component squared, which is negative 160 squared. All right, so this is going to, or this was going to give us 181. All right, so then we're going to obtain 181,934 kilometers per hour. All right, so if you're to consider the direction, your direction was going to be theta being arctan. Remember, we've got opposite here and what? The adjacent. So just consider 160 over 86.603. Don't worry about those negative. What we just need is acute angle. So do not worry about working with a sign that's negative, this and that. All right, so that was going to be 61,575. So you've got 575 degrees, meaning to say our relative velocity, which is velocity of B with respect to A there. Not A, but C. This is C, all right. So that is C is going to be, we got 181,934 kilometers per hour. That's our velocity, we're done. But this is at what? From west to south, that is west 61,575 degrees going to the what? Going to the south. So that was it. So let us just consider more revisions. You can also relate with other questions that you have answered before. The way that you're because already the diagram there is there. The diagram you're already given here, this is your diagram. How are you working if you were given this piece alone? If you're working with this piece alone from your previous calculations, how are you working? Are you obtaining the same thing? It must tally just like what you were obtaining before. It is not supposed to change. So that is what you need to correct as you are revising. All right, let us see 1.2. A boat can travel 15 meters per second in still water. Nothing is affected there. It must come across 80 meters wide river flowing at 7 meters per second to the east. Calculate the resultant velocity of the boat and the direction. So there we need the resultant and also the direction in which the boat must be steered across the river rectangularly. Okay, so we need the resultant velocity in this case. So take note, this is a boat which is traveling in still water. So you get something like this. If you're dealing with the rectangular form, I actually explained about this. I just hope that part is still there. All right. So we have got our boat which is traveling in still water. So this is going up like this. All right. So this is going up. The 15 meters per second is this velocity of the boat. This is where our boat is. So this is where our boat is, and it is going up. Okay, at 15 meters per second. At 15 meters, not this way. This way, you're now talking of the resultant. So the 15 meters is not this side. No. So we have got this part. And let's see, let's just gonna call this point A, then we also call this point B. So let's see what is happening. We are given that it must cross 80 meters wide river. So the 80 meters, that is just the distance that we are given from one point to another of the river, which is 80 meters. Then this river that we are given, it is flowing at 7 meters per second to the east. So the river is flowing to the east. The direction that we are given is to the east side, going to the east at 7 meters per second, which is the velocity of what? Of the river. So the question is, what is going to be the resultant velocity and also the direction when this is steered what? Rectangular, like what we are seeing here. Remember our rectangular format. So the question is, from this part, what are we having, guys? We can simply say that at the end, this is just going to form a triangle like this. So like I said, as this to B, this is our A to B at 15 meters per second. Then the wind, the river now at what? 7 meters per second in the same direction. So it's just going to be a continuation. This is where we are going to have our flow of 7 meters per second. So that's it. So meaning to say, we can calculate our resultant in this case, which is R, and also our theta, just like that. So this is what you had. So the resultant in this case, we can use the Pythagoras theorem because this is a right angled triangle, this one. So from our Pythagoras theorem, it means our R is going to be the square root of what we have in this side. So let us just call this point C. So it is going to be the square root of BC squared plus AB squared. Remember Pythagoras theorem. So R is equal to the square root of, there we've got 7 squared plus 15 squared. So that is going to give us the resultant. So R in this case, if you were to simplify, that was going to be 16,553. This is in meters per second. Then you can calculate the theta according to the diagram. Guys, to take note of what you're given. According to this diagram, what we have there is the opposite. According to this theta, there we have got the opposite. And what is this part representing of AB? This is our adjacent. So meaning to say we can use the tan in this case. If you use the resultant, this is 16, not 15. This is not 15. So you cannot use arc sign because this is not where our R is. Our R in this case is 16,5. If you are to use this one, yes, not 15. 15 is this velocity that is going up. So like I said, guys, I do not know when our department is gonna try to work with this science N4, guys, in terms of revisions. All right. Anyways, the opposite arctan is opposite over adjacent, so that's 7 over the adjacent, which is 15. Not arcsine, but arctan. Okay, so that is gonna be 7 over 15, which is 25,017 degrees. So we have got the direction in that case. So meaning to say, we can consider our resultant velocity to be 16,553 meters per second at. So considering what we have in this case, guys, this is simply, we can consider the north and the east, from the north going to the what? To the east. So it's going to be northeast. So that will be north 25,017 degrees to the east. Okay, just like that. So let's try and revise as much questions as we can just to make sure we have got the same concept in our calculations, same concept. But actually for these values that you obtain, if the values are mistakenly presented, they are going to work with that on when marking there. So do not worry about that to say, so is this going to affect me or what? All right, do not worry about that. So Eric is asked to kick a ball from one end of a soccer field to the other end, which is 100 meters apart, which is one end to another part. So that is our projectiles there. If the ball leaves the ground at an angle of 60 degrees to the ground and takes 5 seconds to reach the other end, calculate the following. So this is the situation that we are having here. The ball is being kicked from one end to another at a certain angle of 60 degrees. So this is our situation, which is taken at an angle of what? Of 60 degrees. Knowingly that we are supposed to have the initial velocity, which we do not have, but we are given the displacement that is going to be taken in this way, horizontally, that is S is equal to 100 meters. We are given this is 100 meters apart, which is the horizontal displacement. This is just a horizontal. This is horizontal, guys, vertical. So we have got what? Horizontal displacement. This is horizontal displacement. So if you're to consider, we have got also the time frame, which is 5 seconds to reach the other end, from this to the other end, 5 seconds. So the question was on 1.31, the velocity at which the ball leaves the ground, which is the initial velocity that we are not given there, which is actually something that we can work with. So remember, we also talked about this part of projectiles, working with the formulas. If you consider the part of the horizontal displacement, which is SH, considering that, I said you can take the horizontal displacement to be given as the U of the horizontal. If you consider this as X, you can write as UX. If you consider as H horizontal, it's fine, times the time of the horizontal that you're given in this case, which is 5 seconds. But we do understand that this UH, which is the horizontal, the one of the horizontal, this U, the part here where we're going to have our UH or UX, the way that you want, is given as U cos theta. So meaning to say, there is something to do with the U that we want, because the question is to calculate the initial value, which is this one. So it is inside this UH here. Inside there is a U there. So you're going to take out that U. So in place of this UH, let's substitute its equivalent. That is U cos of theta times the time that you're given in the horizontal. That's it. So there we need U, so you can calculate this because everything is there. We've got everything there. So divide by the cos of theta times the time. Divide by the cos of theta times the time. So this is going to give us the U that we need. That is, U is equal to SH, the displacement that we have in the horizontal, that is 100 over what? cos of theta, which is theta is 60 degrees. So that's 60 degrees times the time. So that is going to be, remember the time there is what? The time is 5. So that's simply 5 times the cos of what? Of theta, which is the cos of 60, which is the same, guys, as writing as cos of 60 degrees times 5. But you must consider your calculator. This will be in bracket. 60 degrees is not part of 5. 5 is outside of the bracket. So that's why I choose to rewrite this way so that you do not confuse yourself on the calculator there. But there's no need actually, because that you can simplify. So this was going to give us u, which is the initial velocity of 40 meters per second, just like that. So if you're to consider your calculations on projectiles, guys, everything's there. Just go through introductions. The maximum height the ball reaches before it makes its way back to the ground, meaning to say we are considering the maximum height at a certain point. It is going to reach the maximum height. And whenever you're talking about the maximum height, which height is this one? It's a vertical, just like what we had with the horizontal displacement. So this is simply a vertical displacement that we are talking about. And I talked about this maximum height from the formula, that is 1.32. That is, you can take maximum height from the formula. Guys, there's a formula. These formulas, they're not supposed to lie. So just go through your formulas and do revise so that also you have another way of proving, even if you see a certain error or mistake that you are given, that you have from your memo. You can also consider formulas that you had to verify. So remember, our maximum height from this formula is a straightforward. Gonna use initial velocity u that we calculated as it is, that is 40. So we've got 40 squared over 2 times the gravitational acceleration of 9,8 times the sine of theta squared, where I explained that this part here is the same as writing as sine theta raised to the power of 2 from our mathematics. So this is simply the sine of theta, which is the sine of 60 degrees, everything raised to the exponent of 2 or to the power of 2. That was going to give us the H max, which is the maximum displacement. So this was going to be 61,224 meters per second. I also explained on this one, I want you to go through that to calculate the maximum height from a v squared minus uv of the vertical squared over 2g, like that, where you need to calculate the vertical, knowing that our v will be what? Will be 0 from that concept. That will be 0, and this g will be taken as a negative. And remember, the uv is simply taken from what? The uv is simply taken from u, sine of theta. This is now sine this time. So it's simply the u that you got, 40 sine of theta. So I want us to work with that. Divide by 2g. So you see that you must have the same part as what we are having. But the g, like I said, it will be taken at a negative value. You are going to use this as a negative. All right. Remember, you're talking about the maximum height. As you are going up, you are being affected going down. So in that case, you use it as a negative. But in this formula, so you need to know, like the formula that you're working with on this one, just use your G as it is. The formula is already dealt with that. Okay. But in this case, remember, you're back to those linear motion, that part of motion. So you must consider again your formulas. So let us do work with our formulas to check, guys, if these are making sense, like what you are given there, because you'll be having a certain error, seeing a certain mistake, but now to verify, you'll be wondering how. So you must also have other methods that you can use and see if it tallies. So that is what we had on our kinematics. We're gonna work with other questions as we move on.